Welcome back. We're going to start with part B now. So what I want you to do for part B is you need to describe the appearance of the copper 2 sulfate solution and the zinc metal before we carry out the reaction. And the reaction will be allowed to go for 30 minutes. Don't worry, you're not going to have to watch 30 minutes. I will skip to the end so that you can make a comparison. Normally, the color of the solution changes in this experiment, but it was fairly concentrated, and so you might not notice a change. The solution might become a little bit more pale in color at the end of the experiment. And the instructions are essentially the same as for part A. You're going to balance the chemical equation and then state the type of reaction. So here is the zinc metal. You'll see it's nice and silvery, kind of like aluminum foil, but a little stiffer. And this is the copper 2 sulfate solution. And I drop the piece of zinc in there. At this early stage of the reaction, there's really not much to see. Now, initially, it might not look like much has happened after 30 minutes, so we have to take a really good, close look at what's going on. You might be able to notice that the blue solution is just a little bit more pale, but the main difference occurs down in the bottom of the test tube. Let's let this focus. And there we go. So you'll notice the zinc metal has been encrusted with something that looks very much like moss. And what that really is copper crystals. So the copper ions in the solution have become copper metal, and they have grown on the zinc metal surface. In part C, you're going to see 3 different metals being added to hydrochloric acid in separate tests. You'll see that some of the metals might react very vigorously, others slowly, others maybe not at all. So on your report sheet at the top of page 82, you're only going to want to balance the reactions which actually occur. So please, if you do not see a reaction, just cross out the products with a line and write NR, which is no reaction. Don't even try to balance the reactants. That wouldn't make sense. So just cross out products, write NR. And then identify the type of reaction that you saw on the line. And if there is no reaction, just write NR on the line. I'm going to take zinc metal and drop it into the hydrochloric acid solution. And what you're going to see here is taken over the course of several minutes. If we first go ahead and look down the test tube, we see that there are bubbles on the surface of the zinc after a few minutes. And then we see bubbling. The bubbles contain hydrogen gas. Skipping forward in time, we see that the bubbling has become a little bit more aggressive, and there's some fairly large bubbles on the surface of the zinc. Now we look at copper being added to hydrochloric acid. And if you look at this closely, you might see a bubble on the surface, but that's just an air bubble. Nothing really is happening here. So I'm going to let this sit for a while and then come back and look at it again. Alright, so this was 15 minutes later. We don't really see any change at all. Now I'm going to drop a strip of magnesium into the hydrochloric acid. Clearly there is a strong evidence for a chemical reaction. The gas, again, is hydrogen gas. And you can see the magnesium metal skating along across the surface. You'll also notice droplets of water forming on the sides of the glass. Some of that is water that has been kicked up by the magnesium as it moves across the surface. And some of that is steam from some of the heat that's released during the reaction. I'm going to go ahead and touch it to my skin. And while it's not burning hot, it definitely is warmer than when the reaction started. We're now going to look at part D1, and you will see solutions of calcium chloride and solutions of sodium phosphate. And you want to describe these, and the kinds of words you want to use in your description are as descriptive as possible. So if it's white and cloudy, you would have a color and kind of a texture to the solution, whether you can see through it or not. Water, or anything that looks like water, is clear and colorless. And then, as before, you're going to want to describe what you see as evidence of a reaction if one occurs, and then identify the type of the reaction. So here you see the calcium chloride solution in the test tube on the left, sodium phosphate in the test tube on the right. I'm going to combine them. And clearly a change resulted from that. And here is a closer look at that product. Moving on to part D2. You'll want to start by describing the solutions of iron 3 chloride and potassium thiocyanate, just like you did with D1. And thiocyanate is a polyatomic ion which we haven't discussed to this point, and its formula is SCN. So just as before, you want to describe any evidence of a reaction, and then identify the type of the reaction. We have the iron 3 chloride solution on the left and the potassium thiocyanate solution on the right. I'm not going to combine them. And we clearly see a change. Now let's take a look at part E. So you're going to want to start by describing the appearance of the hydrochloric acid, which you've already seen at this point, and then the solid sodium carbonate. Describe the evidence of a reaction if you see one. And then there'll be a second part on this experiment. I'm going to take a piece of wood and ignite it to form a burning splint. And towards the end of the reaction, I'm going to go ahead and put that burning splint into the test tube. Now the wood is undergoing a combustion reaction. And what does that mean? What gas is it reacting with? Combustion, remember, means reaction with oxygen. So it's combusting before I put it into the test tube. And then you'll want to describe what you see happening once I put it in the test tube. And then there's a spot for you to offer a fairly short explanation and use a complete sentence in giving your explanation as what you see happens. Don't just say what happens, but try to explain what must be happening, considering that combustion is the reaction of something with oxygen. And you'll want to balance the equation, identify the type of reaction before the burning splint was added. So the type of reaction is not combustion. That was only for the splint. You want to talk about the type of reaction that's going on in the test tube. Okay, I'm going to take some of the sodium carbonate here and put it in the hydrochloric acid solution in the back. And you can clearly see that vigorous bubbling occurs. And when you look on the report sheet, you will see that bubbling comes from the formation of carbon dioxide gas. Here I'm igniting a splint of wood, and I'm blowing it out to get it so it's not quite so large a flame. Not very successfully. And I'm going to start the reaction again by adding a little more sodium carbonate. And now I put the splint in. And you'll notice that it stopped burning actually the instant it got to the top of the test tube. You'll want to begin part F by describing the appearance of the hydrogen peroxide solution, that is H2O2. It's a 3% solution in water, very similar to the hydrogen peroxide you would buy at the store. Now, hydrogen peroxide will turn into water and oxygen, but it is very slow, and this reaction could take years. And obviously we don't want a video here that is years long, so we would like to speed up the reaction. And to do that, I'm going to add a catalyst, potassium iodide. Now, the catalyst is not considered to be a reactant because what happens is the catalyst speeds up the reaction, but it is not used up or consumed at all in the reaction. And in fact, I could use that catalyst over and over to carry out the reaction. And so we write it above the arrow because we don't include it in the balancing process because it's not used up. I'm going to add the potassium iodide solution to the hydrogen peroxide. And let them sit for a few moments. The color comes from the potassium iodide. It's not actually evidence of a reaction, it's just the color of the substance itself. And initially we don't see anything very exciting going on. Let's give this some time. After a few minutes, we start to see some bubbling occurring. Those bubbles are oxygen gas. Finally, before I let you go, I'd like to give some advice on completing the rest of the lab report because this experiment tends to have some questions that are a bit tricky. So let's take a look at the pre-lab study questions on page 79. On question 4, off to the left part of the table, you're asked to balance some equations, and you're not really given any room in which to do that, which creates a bit of a problem. So what I'd like you to do is just very carefully and very neatly write the coefficients above and slightly to the left of each formula using small numbers, but large enough that we can read them when we grade them. And it would really help if you wrote these equations on a separate sheet of paper first, balanced them, so you're not writing numbers and erasing them and writing them and erasing them and making it very difficult to grade, so that way we can see the numbers very clearly when you go to write them down. Looking ahead to question 5A, also on the pre-lab study questions, just wanted to give you a hint on this. The product is an ionic compound, and it contains ions potassium and nitride. And you figure out its formula in exactly the same way as you did in the last experiment, experiment 6, in part B. And in fact, that might be one of the questions in part B of experiment 6. On 5C, don't forget that the formulas of all ionic compounds must add up to 0. You need to double check that. You can't just drag numbers with you from one side of the equation to the other. It's the balancing which ultimately will be concerned that with you're having the same number of each element on either side. So for example, the product can't be AlSO4, aluminum sulfate. That's not aluminum sulfate because aluminum always has a 3+ charge. Sulfate always has a 2- charge. Putting those together would give you a +1 charge. So the formula would need to be written so that you have a total 0 charge. So think very carefully about that ratio. Looking at the next one, 5D, remember that the charges of ions do not change in double displacement reactions. Sometimes these problems say replacement and sometimes they say displacement. That means the same thing. And again, make sure that your ionic compounds make sense because their formulas need to add up to 0 and the cation is always written before the anion. For 5E, you might have difficulty predicting that product, but if you go back and look on page 75, you'll find that there's a very similar reaction. It's just a change of one element, but the rest of the reaction is the same. Skipping ahead, take a look at question 3 on page 84. And you are asked to write the states for these reactions, so I want to just give you some hints on that. So for question 3, part A, it says liquid pentane, so it's obvious that pentane is a liquid. Everything else, the oxygen, the carbon dioxide, and the water, are gases. In a combustion, you give off so much heat that the water is vaporized as steam. For part B, this might not be obvious, so I want to go over it. You're taking sodium metal, and sodium is a solid. You're putting it in water, and water is a liquid. And when they react, it forms sodium hydroxide, which stays dissolved in the water. So we write AQ for the state. It is aqueous. And then it also produces hydrogen, which you know is a gas. And then for part C, everything except oxygen is a solid. Oxygen, of course, is a gas. And then let's look at question 5. So for A, you need to remember from when we discussed an experiment in 6 that the only ion that zinc forms has a 2+ charge. It's one of those constant charge ions. So when you're figuring out the product, remember zinc is 2+, and the total charges have to add up to 0. For B, the product is not H2Cl2, it's HCl, hydrogen chloride gas, which is what is dissolved in water to make hydrochloric acid. And don't forget, you need to balance the reaction. For part C of question 5, you've already seen an example of this reaction earlier in the lab instructions, and I just talked about something very similar to this on the previous slide. So go hunt down the closest possible reaction to this. And heat is needed in this reaction, so be sure to write a delta over the arrow. And then finally, for D, remember that ions, again, do not change their charges in a double replacement reaction. You might want to go back and review these last 3 slides one more time so that when you're looking at your report sheet, you're not making any critical mistakes and you're maximizing the points that you earn on this experiment. Thank you as always for watching the video. I hope you enjoy it. And that will be the end of the experiment 7 video.